Alrighty, good morning. You don't know this, but this is try number 2. So we're going to take a look at the first derivative test with parametric equations today. And we're going to take a look at the parametric equation x equals 2 cotangent theta and y equals 2 sine squared theta. And by using the first derivative test, we're going to try to find some relative minimums and relative maximums of this curve. And to draw this, we're going to take theta between 0 and pi. We can even put equals 2 in there for right now. And so if we're going to do the first derivative test, the first thing we have to do is take the derivative. So dy over dx equals. And the derivative of a parametric equation, the first derivative at least, is very easy. You take the derivative of y with respect to theta and you divide it by the derivative of x with respect to theta. So here is our fraction. The derivative of y, 2 sine squared theta, we have to first use the chain rule. So this 2 in the exponent is going to multiply the 2 coefficient. So that will give us 4. And then the inside, sine, does not change. But then we have to take the derivative of sine, which is cosine of theta. So there is the derivative of y with respect to theta. Now we have to take the derivative of x. So 2 cotangent theta, the 2 is going to come out. And cotangent theta, one of the derivatives you need to have memorized is cotangent theta. When you take the derivative, you get negative cosecant theta. And so there is our derivative. To use the first derivative test, we want to know when is that derivative equal to 0. That's when you have a relative min and you have a relative max, which actually makes this fairly easy because this fraction will only be 0 when the numerator is equal to 0. A denominator can never make a fraction equal to 0. And so we have 4 sine theta times cosine of theta equals 0. And so when does this equal 0? Well, the 4 doesn't matter. When does sine of theta equal 0? When theta equals 0. Sine starts at 0, 0. When does cosine theta equal 0? Cosine starts at 1 and comes down towards the x-axis and hits the x-axis at pi over 2. And then one other one we might check, since we are going all the way to pi, sine will again be 0 at theta equals pi. Alright, now that we know when our derivative equals 0, we can set up a sine chart. So up here on the right, I will start our sine chart. So we have to check 0, we have to check pi over 2, and we have to check pi. Draw these down. And our factors are sine theta, cosine theta, and then cosecant theta right here. Remember, we have to use the entire derivative for the sine chart, all of it. I'm going to rewrite cosecant theta, might be a little easier, as 1 over sine, oops, I did forget the squared, didn't I? I think I said it, but I forgot to write it. Sine squared theta. Thankfully that hasn't changed anything. And there's actually one more factor that we have to take a look at. Right here. Our derivative is being multiplied by negative 4 over 2, which is negative 2. We have to take a look at all of those. So let's finish our sine chart here. It should be pretty quick. Sine theta is 0 here, then sine becomes positive and is 0 again at pi. Cosine theta is 0 at pi over 2. Before that it is positive. After that it is negative. 1 over sine squared, well, sine squared is always going to be positive. That's kind of nice. And negative 2 is always negative. And so then we take a look at our sine chart. That is negative, and that is negative, then positive and positive, as this is our 0, 0, and 0. Did I get that right? No, I believe I messed that up a little bit because I forgot to do this up here. Sine of theta. Got to make sure you don't miss things like that. I didn't write those down. So sine before 0, it is actually negative, and then after pi, it is negative. So that does change things. So this first one becomes positive, and the last one becomes negative. So looking at this now, this first piece here, well, that looks like a relative max. This one looks like a relative min, and this one looks like a relative max again. Here's where the curveball with parametric equations comes in. Those are all wrong. That is not a relative max, that is not a relative min, and not a relative max. To show this to you, try graphing this set of equations. Go from 0 to pi for t and see what you get. It is not going to go max, min, max at all. And so I can show this to you on Wolfram alpha. Here is what that plot looks like. Hopefully you can get that on your calculator or something fairly similar to it. There is definitely a relative max, and then we have two asymptotes as minimums on either side. That's a little weird. So let me draw a quick picture of that on the screen and we can talk about why that is. So here is what Wolfram alpha tells us the graph looks like. We have an asymptote, a max, and another asymptote. The thing is, I just drew that graph from left to right, which means we would read our sine chart from left to right. However, when you graph it on your calculator, you should see that the orientation of this is right to left. Your calculator starts drawing on this end and then draws to the left. That means that is the way you have to read your sine chart, from right to left. So we have to go this way, and that changes everything. So if your derivative is going from negative to positive, negative to positive, that would be a relative min. If then your derivative goes from positive to negative, that would be a relative max. If it goes from negative to positive after that, that would be a relative min.
Again, we are running on the off-schedule stage, so class will be dismissed at 9:56. Again, it will be 9:56.
And sorry about the interruption there. Can't redo this video, this is the second time. As you can see, that matches the graph much better. We have a relative min over here. We have a relative max, that at least looks good, and a relative min over here. Although an asymptote really isn't a relative minimum because it never actually gets to the minimum value. And so what we have to do now, one more curveball, is do these actual points exist? If they're not actual points, then there can't be an actual relative min or relative max. Hopefully you see that this one here and this one here are completely out. They are asymptotes, but we should check them anyways. So we need to check theta equals 0, theta equals pi over 2, and theta equals pi. So in your graph, hit trace, and then trace those three values. You'll find when you hit theta equals 0, it will say x equals blank, y equals 0. Because our asymptote is approaching 0 going this direction. We are getting closer to 0. But we never actually get there, which is why there is no x value. It's missing. And then if you try the next one, you'll get x equals blank, y equals 2. So that looks like it would be this point up here, which while we do have our maximum value of 2, there is still no x value because x is undefined. So again, we don't have our relative max even. And the last one, if you do it, x equals, if you plug in pi, you get x equals blank, y equals 0. That one also does not exist, but you can see it is again going to 0 with our asymptote. So you know what the limits are going to, but because there is no point, there isn't actually a relative max. It's a very unsatisfying example, but it shows some of the weird characteristics of trying to use the first derivative test with parametric equations. There's a couple of curveballs. You have to look at the orientation of your graph. Are you graphing from left to right, or are you graphing from right to left? That will determine how you read your sign chart. And then, do the points actually exist? If they do exist, you can have a relative minimum or a maximum. If they don't exist, then sadly, you can't. I'll let you plug in those values, 0, pi over 2, and pi. So hopefully you can see when you plug in 0 to x, or sorry, if you plug in 0 to theta, you can see why that would give you an undefined x value, and the same is true for the other two also. Hopefully you can see that by looking at the definition of cotangent. I hope that made sense for you.